I'm actually going to be inductive on this part. What do I mean by vectors in a space? I mean physical quantities that have direction in three-dimensional physical space. So, for example, force, momentum, angular momentum. I'm just picking like 3 random ones. Velocity. There's all kinds of things that have direction. These are physical these are physical quantities that have direction in three-dimensional space. These quantities relate to one another in particular ways. How do they relate? How do they relate? Let me look something up so that I can present this really efficiently.
Okay.
What I'm about to show you is probably going to be familiar. But I encourage you, and I'm sure you won't have trouble doing this, I encourage you to focus on its physical meaning and not its connection to things you've seen in math before. Okay? So here's an example. F1 plus F2, let's say you're adding 2 forces. If you add 2 forces, if you add them in opposite order, it's the same force, right? Another thing worth noting, when you add 2 forces, it has a resultant. So like 2 forces added together has the same effect as some other force. Let me show that. F1, F2. Let's get rid of the other things because we don't need them anymore. F1 plus F2 is the same as some FR, resultant. So, that's the way forces add up to one another. That's just how it goes. That's the physical nature of these actions. They exist in 3 dimensions, and they add in a certain way. That's a property of physical vectors, okay? All right, what's another property? Another property is that there's a force that's 0 quantity, and if you add that force to a force, you get the same quantity, okay? What's another property? For any given force, there's a negative force that if you add those 2 forces, there's a certain kind of force that if you add it to that force, you get the 0 force. Okay? Now, these are all, so I've been encouraging you to think, there's a few more, but I'm going to stop. I've been encouraging you to think about these as physical rules, and these are just obvious physical rules. They're probably familiar to you, right? These have been introduced to you as mathematical rules also. Have you seen these before?
Yeah.
Yeah, these are the axioms of linear algebra. Or actually, they're the axioms.
Yes.
They're the So what are well, I think that's not quite what they're called. They're called, let's see. This is calling them the axioms of real vector spaces, okay? I'm going to just I guess I think I agree with that name because I think they're saying like real, they mean like non-imaginary, non-complex, I think is what they're talking about. Okay? Yeah. Now, what I have said, I've been focusing on forces. Okay? These are so let's not connect it to linear algebra just yet. Let's take a step back. These are rules of physical space. These are, hold on, I need to think, I'm kind of creating terminology right now. These are rules of physical vectors. Okay? What I mean by physical vectors is 3-dimensional vectors that represent physical properties that have direction. So examples being force, velocity, angular momentum, blah, 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 all of those. Understanding why angular momentum is a vector, by the way, is very fun. It's difficult to understand why angular momentum is a vector. So if you haven't figured that out, we'll do that sometime. Because it's not clear, like, why would you think of this as a vector? All it is just like how much it's spinning, right? But we'll get into it sometime. So those are all vectors. They have a three-dimensional characteristic. And so I'm calling these physical vectors because they're real physical properties. In contrast, in linear algebra, I'm going to call these things, hang on, I'm going to call them abstract vectors.
Okay.
Okay? They're different from physical vectors, but they share some of the same properties. Now I'm going to scroll up, and I'm going to return to these two functions. Or not just these two functions, but I'm going to return to every function that could occupy this space. All these functions, it turns out that they relate to one another in ways that are similar to the way physical vectors relate to one another. Their relationships obey all of the rules of linear algebra. Of real vector spaces. Or I'll call them abstract vector spaces. Okay? Abstract vector spaces are exactly like physical vector spaces. There's only one difference. There's two differences. Number one, abstract vector spaces are not necessarily physical. They don't necessarily represent things that actually are out there in reality with 3 dimensions. Okay? They're just a mathematical construct. Okay, so that's one difference. The other difference is that an abstract vector can have as many dimensions as you'd like. It's not confined to 3. It could be 3, but it can be infinity. And we're seeing its infinity in this example with all of the different Fs. Okay? Now, why is this important? The reason this matters...
The infinity part, I kind of didn't get that one.
This... physical vectors have 3 dimensions. These abstract vectors have an infinite number of dimensions. So, why do we keep track of these axioms of abstract vector spaces? It's because whenever a set of mathematical objects relate to one another in accordance with these axioms, then we can use our intuitions about physical space to understand the relationships between the elements. And that's powerful because man is really good at just thinking in terms of physical space because we live in physical space. Yeah. Yes. So we get to leverage that intuition to deal with the information, basically. That's the power of linear algebra and abstract vector spaces.